All right. Bismillahirrahmanirrahim. Yesterday we started talking about learning. We said there are three basic types of learning algorithms. What were those? Supervised learning, unsupervised learning, and reinforcement learning. Okay. So we said we are not going to talk much about reinforcement learning for now. In supervised and unsupervised, we talked about unsupervised first, and I gave you example of an algorithm for unsupervised learning, which is k-means, and then I showed you an example of how to use k-means in the bag of words approach, which is actually a classification approach. So it's not, bag of words in its entirety is not a unsupervised learning approach. That would be an incorrect statement to make, right? Bag of words we used for image classification, which is actually a supervised learning problem. I still need to learn those feature vectors of which feature vectors belong to which. But as a step inside it, we used unsupervised learning to actually come up with the clustering of our words. To come up with the dictionary words or visual words concept. Okay, so most of the rest of the lectures we are going to concentrate on supervised learning. Okay, which is where you have training samples available. Okay, so you have labels available for your training samples. Yeah, that's training samples are available in unsupervised also, but you don't have labels, so you have to cluster them. Here we are going to use the labels which are available to learn a classifier. Okay, now our goal is to go towards understanding of deep learning. So what I'm doing is I'm gonna which is a supervised learning approach most of the time. There are unsupervised versions of deep learning also that we might talk about, but to be able to understand that, we need to get some concepts about learning, about supervised learning under our belt. So I'm going to go through those rather quickly and then talk about them in detail when we talk about neural networks from the next week, inshallah. Okay, all right. So here's an example of supervised learning. Okay, so let's say that we wanted to have an algorithm to accept or reject a student for admission in a university like LUMS. Okay, so that's our problem. We will have applicants applying to the university, and it's let's say right now done manually, but we want to make that system automatic. We want a computer system to learn how to make that decision. Okay, so that's a classification problem. It's two category classification: accept or reject. Okay, so I want to come up with that label: accept or reject, yes or no label. Okay, and for simplicity, I'm only going to consider two features, even though there are a lot of features on your application packet. The university makes you write an essay, and what are your interests, and all sorts of questions that they ask you. But we are going to just simplify and say there are only two things. There are test scores and pass grades. Past grades are like your O-level, A-level grades, some summary of that grade, and test score is you come for an admission test and how you perform on that day. Okay, all right. So there is a student one who scored 9 out of 10 on test and 8 out of 10 on grades, previous grades. This 8 out of 10 is some summary of their O-level, A-level score or whatever. Okay. So it looks like we should accept this student, right? He seems like a good student. All right, so we kind of accepted that guy. All right, now there is a student 2. He scored 3 out of 10 on test and 4 out of 10 on grades. It looks like it's an easy decision, we'll kind of get rid of that student. Okay, no, you're not accepted. All right, but what about this guy? So he has a 7 out of 10 on test and 6 out of 10 on grades. Okay, so I have like a question mark here of what to do. So what should I do? I can set some threshold, yes. Based on what? Yeah. Sorry? I can't hear you. Please speak louder. Okay, so what both of you suggested is let me average these two out, and then put some threshold. In machine learning language, what you are saying is let's do dimensionality reduction. You have two features. Instead of that, let's use one of them. Okay, I really don't have to set a threshold. If I want to set a threshold on just one, I can set a threshold on two, which will be like a weighted combination of these, and so I can have like a line cut through this two-dimensional space if I want to. Okay. I'm not. I didn't say that. Right. So what I want to propose is that, okay, if I'm faced with this decision, maybe one thing I can do is let's look at some correct admission decisions which were taken last year. Okay, and I can compare this score to that. And if this score looks like, well, we didn't accept these types of guys last year, maybe I shouldn't accept this. And if it looks like maybe this is a clear accept based on last year's scores, maybe I should accept this guy, right? That's the notion of training data. I'm giving you example of last year, but the notion of training data is somebody has already labeled your set for you. Okay, so I'm going to look at this this point, which is a student in this case. I'm going to look at this data point in the context of already labeled data. That's the notion of supervised learning. Agreed? All right. So that's your guy here, which was a clear accept. Because I have two features, test scores and grades, this is a two-dimensional, what we call feature space. Okay. Now, the feature space is some properties. The vectors that span feature space are the range of values of some properties of your data point. Okay. In this case, it's a student. Your data point could be an image. These feature space vectors could be, let's say, the coefficient values of PCA of that image. It could be the hog features. For that matter, it could be actual raw pixel values. I could say, let me treat raw pixel values as features. Okay, which is the native feature space on the identity axis. Okay, so in machine learning classification examples, we always talk about a feature space, some place in which I can place my data points. And the feature space can be very high dimensional. Like if I use every pixel of the image as one feature, every pixel value as one feature, then if the image is 100 by 100, then my feature space is 10,000 dimensional. Okay. Now, this is the guy on that feature space that we said, well, that looks like a clear accept. It's 9 out of 10 on tests, 8 out of 10 on grades. This is a guy which looks like a clear reject. He's 3 out of 10 on tests and 4 out of 10 on grades. And then the question I was asking is, where's this third guy, which is like, oops, where's the third guy? Let me see. The third guy is going to be 7 out of 10 and 6 out of 10. So he's going to be here. Okay. Now let's say I have data from the previous year. The data from the previous year, the orange guys are those who got accepted. So this is my labeled data. That's the hallmark of supervised learning, that you have some labeled data available. Okay, so the orange guys got accepted and the gray guys got rejected. Yeah. Yeah, assume that the data was from the same year. Your training data should have similar characteristics to your test data, statistically speaking. Okay, if it is not, then you will run into problems. Yeah. Yeah, that's true. That's what I'm saying. In machine learning terms, I'm saying your training data and test data should have similar statistics. That's exactly what you said. What if they have dissimilar statistics? Well, that's not good training data then. Okay, I'm motivating the example by previous year, but really there is no gap between these two. Really, I have some data set out of which I have some data set which is labeled, and I have statistically equivalent data set which is not labeled, let's say, and I want to label that. Okay. All right, but I'm just motivating this example. So let's say this is the data that was already labeled. Okay. What I can do then, what I can learn from that data is, so this is training data, it's already labeled. What I can learn from the data is some sort of classifier function. Okay, this particular example that I'm showing you now is what we term as a linear classifier, because the Decian boundary, this green line, the Decian boundary is linear. Okay, how did I find that Decian boundary? I tried to find out of all the possible linear functions that I can draw, I try to find that one which gives me the best classification accuracy on training data. Okay, and we'll look at that process in detail of how we do that. It turns out that this problem is very similar to a regression problem. I tried to minimize the error between my data sets. All right. However, once I find this boundary, so this is the Decian boundary. Once I find this boundary, I can see where my point lies. Okay, if that point is on this side of the boundary, where we have the gray majority, I will say, well, that's an accept Decian. And if this point is on the other side, I will say that's a reject Decian. Okay, so I did not do any dimensionality reduction that you were suggesting. I just took the original feature space that I have, and in that feature space, I came up with a boundary. Agreed? All right. So so that's going to be, once I have the boundary, I'm just going to get rid of the training data. I don't need that anymore. All I needed was the classification, the model for the classifier, which in this case, in this particular example, is a boundary. You can't actually always get rid of the training data. Some classifiers actually are defined by the training data. There are some non-parametric form of classifier. But I'm just giving you this example. In this example, once I found the boundary, I don't care about the training data. The training data existed only for me to learn a good boundary, okay, which is the Decian boundary. And now I can say that this guy, so this is a linear classifier, the type of discriminant function. What's a discriminant function? It's the function that distinguishes between your classes in the feature space. It splits your feature space into regions, which each region belongs to a class. Okay, so this is a linear discriminant function. It's an important category of discriminant functions in machine learning, and so I will now classify that guy as an accept. Okay, now maybe somebody comes and says, well, a linear discriminant function is not good enough, okay, because anybody whose grades is less than 2 out of 10, we are not going to accept them regardless of how well they score on the test. Okay, let's say somebody makes that observation. The argument is, well, test is 1 day's performance and these grades are like 2 years of performance. Maybe I should rely on them more, or I can use that as a cutoff that below 2 out of 10 you are not even eligible to be considered for admission. Okay, what that means is that my my discriminant function is going to be like this. I learned that discriminant function to distinguish, but I put a threshold on 2 out of 10. I'm going to not go below that, so that my reject class actually expands into this region also. Okay, this is an example of a nonlinear discriminant function. In this particular case, it's a piecewise linear function. Actually, we call it's nonlinear, but within the category of nonlinear functions, it's a piecewise linear function. It's made out of a combination of 2 linear functions. Okay, and then one side of this function is it divides the Decian space into 2 classes, the feature space into 2 classes. Well, because this was a 2-category problem. If it was a 10-category problem, my discriminant functions should divide my space into 10 classes. Okay, and now you give me a new point, I'll just measure its features, see which region it lies in, which side of the discriminant function it lies in, and I'll decide. Correct? Yeah.
If it lies just on can you make this?
Yeah, you will decide one way or the other. You can say greater than equal to that function is one side and the other. Sorry?
Would it be correct?
What's correct?
If the point lies just on
You are defining this function. You could say on the line means that way. Well, by the way, this is continuous data. if this is continuous data, the way I've drawn points, then the probability of exactly lying on the line is 0. Right? That's an infinitesimally small accurate point. But even if it does, you have quantization on your data, it does, just decide one way. Decide that on the line I'll give the benefit of doubt to, let's say, accept. There's nothing wrong with that. All right. Okay. So this is my discriminant function. Well, if I look at this data again, I really don't have to, if I allow nonlinear functions, I really don't have to worry about, okay, I can only make linear functions or nonlinear functions. I could make something like this, okay? And maybe this is a better function for my problem, okay? Notice that this function has less error rate than the previous one, okay? By error rate, I mean, okay, how many points in my training data set are actually misclassified? One here, there is one orange on the wrong side, right? And there are 1, 2, 3 gray, or 4 gray on the wrong side. So I could say the accuracy of this function on training set is 5. That's actually, we term that the misclassification rate. The misclassification rate is 5 out of whatever was this total, okay? And the goal of my training algorithm, where I'm trying to find this function, is often to minimize the misclassification rate, okay? That's called the cost function or the loss function. We have some sort of loss function that we are trying to optimize over when we are doing training, okay? All right, so this is a nonlinear discriminant function. It's an example. Maybe it could be, for example, a higher order polynomial. So maybe this is a polynomial of order 10, okay? And so what are my unknown parameters here? It's the coefficients of that polynomial. Once I decide I'm going to work with polynomials of order 10, I don't know those coefficients. I can solve for those coefficients in the least square sense using my training data. Agreed? Okay, maybe I do like even better. Maybe I come up with a function. I say, well, why order a polynomial of order 10? I'm going to use a polynomial of order like 30, right? And then my misclassification rate is exactly 0, which means the strategy that I took here is the category of my discriminant function that I want. I said, okay, I first tried a line and I got some error, and I said, okay, let's try some higher order polynomial, and I still got some error, less than the original one. And then I said, well, I'm not happy, let me try even higher polynomial, and I kept doing that till I get exactly 0 error, exactly 0 misclassification rate, okay? Now this might actually be an overfit of the data. What do I mean by overfit? These guys here maybe should have been rejected, right? It just happened that last year they got lucky, maybe for some reason or the other, and they got accepted, okay? If I do this too much, maybe I have an outlier point here, okay? That was an outlier in my data, but if I keep on overfitting, sooner or later I'm going to find a function wiggling through just to include that. And that would surely be a bad idea, right? Maybe I'm just fitting to outliers in my data, right? So just keeping on increasing the flexibility of your model just to get perfect scores on your training data might not always be a good idea, okay? Which is why what you do to protect against overfitting is that the available data set is divided, the available labeled data set, which is for training, we actually divide that into 2. We say there is a training set and a test set, okay? And then, so this is your available data, you're going to split it into a training set and a test set, okay? And the test set is then used to learn the discriminant function, okay? This split might not be equal. Why is it not equal? Because I want to retain as many things in my training set as possible so that I can learn well, okay? but one might argue then your test result would not be very accurate. Okay, because you have very small test set. So this is the problem we'll come back to, how to decide on the size of training set and test set. But let's say I had some split. Now the test set, I'm not going to let the training algorithm see it, because then there is a chance that the training algorithm might overfit. So I'll train and then test on an unseen set of data. Train and then test on unseen data set. Okay. The error, when I say this is my current error, that will be measured on the test set, not on the training set, so as to protect against overfitting. Okay. So the idea is that if we do end up overfitting on the training data, the training error would be actually low, but the test error will increase, and I will know that I'm kind of overfitting. Okay. All right. So this is what typically happens: training versus testing error. If I'm measuring error on the training sample, and on what do I have on the horizontal axis? I have model complexity. Let's say the order of the polynomial, which is my discriminant function. All right. So as so let's say think only about the gray curve. As I keep increasing the model complexity, my training error must go down if I'm doing a good job at training. Okay, it should continue to go down. A polynomial of order 10 can always do as well as a polynomial of order 5, because actually a polynomial of order 5 is contained within the class of polynomial of order 10. Okay, so that's the argument, that the training error should continue to go down, or in the worst case it should just flatten out, not improve much, but you can just continue to decrease it. Okay, but on the test sample, there's going to be once you start overfitting to your training data set, the test sample error is going to start to increase, because more and more points in the test sample are going to get misclassified because of that overfit. Okay, so really in this case, the model complexity that I should have should be somewhere here. That's kind of like the optimal model complexity in this class of models, in the class of discriminant functions that I'm choosing here. All right, any questions on that? Shahrukh. Why does an overfitting happen? So this is kind of like an example of overfit, right? Why is this bad? Because, well, the actual generalization might, why should students getting admitted to lumps be favored in this region? What's so special about that? Right? It just happened that you got an outlier point in your training set. That's why you moved the boundary that way. Okay. So overfitting is when you are fitting too much to your training data, which does not generalize in general. I mean, it will not generalize to the general characteristics of the data set. Okay, so with that introduction, let's talk about images. So I have a data set of images and their labels. There are some cat images, some dog images, some mug images, and some hat images. Okay, these are labels. So this is labeled data set. So this is a training data set, and I'm going to use machine learning to train an image classifier, and I'm going to evaluate the classifier on some test images that are unseen. Okay, that's the strategy. Okay, so in general, I'll have like two functions, train and then predict. The train function takes in training images and some trained labels, and it returns a model. Okay, so these two, the images and the labels, form the training set, because this is supervised learning, and it returns the model. And then the predict is gonna take the model and some other images, some test images, and it's going to return test labels. Okay, labels on this test images. Okay, and then we are going to use those to measure error and say this is how well my classifier was performing. Okay, now we look at first a very, very simple classifier. before we come back to linear classifiers like the example I showed you, or some other complicated discriminant function classifiers. By the way, in machine learning, some of the most successful approaches in the last 30 years or so have been, overall in AI, some of the most successful approaches in the last 30 years or so have been those of statistical learning, statistical pattern recognition, or what we also sometimes just for short form call machine learning, but those that are based on learning some statistically from your data. And in supervised learning, some of the most successful approaches have been those that are based on learning discriminant functions. CNNs, convolutional neural networks, being one of them. Okay. So, I will come back to this as we talk more about other approaches. Yes. Yes, that's what we are saying. We need a lot of training examples to then predict something. Yes. Learning discriminant functions from training data is statistical learning, because you are learning some sort of property of your data. Sorry? Yeah, like I talked about expert systems, for example. That's a learning algorithm, but not a statistical learning one. Okay. If you look up, let's say, an AI text, a standard AI text like Russell and Norvig, they discuss a lot of methods which are not statistical learning. Okay. All right. So here's one very simple classifier, but it works. It's like, this is one. Yes, go ahead. Okay, so that's a good question. If I have some data that I can visualize, right, because I can plot it, then I can just look at it and say, oh, that looks like a good classifier, and code that in an algorithm. True, like you were able to see in this example, but you can plot things only which are two-dimensional, or at best three-dimensional. And then what are you going to do when I give you an image that has 10,000 pixels, so it's 10,000 dimensional? What are you going to plot? Okay, like these images. Okay, this is the problem. It's a real problem. You have to categorize them. What are you going to plot? Right? So it's the challenge of working in high dimensional spaces, which is not easy. Okay. Actually, because you asked me a divergent question, I'll give a divergent answer to this also. There's people struggled with this problem of trying to visualize high dimensional spaces, because you are right. If I can visualize a high dimensional space, then maybe I can say, well, this is what is happening in my data. I can understand a lot about my data, or the characteristics of my data, even the statistics of my data, if I can visualize them, right? So this human limitation that we can't see beyond 3 dimensions, right? People struggle with that a lot and try to come up with a lot of different techniques to be able to view that, right? So there's a very interesting paper in like 70s or 80s which said, okay, what if I'm given like 15-dimensional data or 20-dimensional data? How can I see which data points are similar to each other, which are not, and do they cluster and do they not cluster? How can I see that? And then those authors, they played on this ability that humans have the ability to recognize faces. The capability of mankind to see subtle difference between faces is actually very pronounced. In fact, now we have found out by neurology and brain studies that there is like a separate processor in the brain to distinguish between faces. So subtle changes between a human face, I can recognize them, but subtle changes in this microphone I'll probably ignore, because I'm not trained. I don't have like special part in my brain trained to look at subtle changes in this structure. Okay, so they said if that's the case, what we are going to do is you give me this 20-dimensional data. Every row of this data set, there are 20 columns, right? Every row of this data set I'll convert into a human face. Okay, so they made a drawing. Okay, now in the size of the eyes was one parameter, controlled by one parameter. The distance between the eyes was another parameter, and the angle of the eyebrows was another parameter, and the shape of the nose was another parameter. So they encoded like every single bit of that data set into a face. And then they said, look at these faces, and if they look similar, then the data points must be clustering, and if they don't look similar, then they would not be clustering. Okay, so this is taking this to a rather extreme that I want to visualize high dimensional spaces, and so I mapped my data points into something very recognizable, so that perceptually in my brain, if two things have large perceptual distance, the hope is that they should also have large distance in that data space. Okay, so just to answer your question, I'm saying people have tried really weird things to try to visualize high dimensional spaces. It depends on the data set, and I mean it's really limited in a lot of ways. One thing now we do often, just to get some sense of how my data looks like, is that we project it into a really low dimensional subspace and try to see that. It doesn't tell you all the characteristics of the data. It could be that your data is well separated in a high dimensional space, but when you project it, it looks all muddled up and so on. But at least it gives you some idea. So it's a very typical trick. You do PCA, find the first 2 or 3 dominant eigenvectors and visualize your data on that, and then get some sense of how my data looks like. Okay, but as far as classification algorithms are concerned, we'll show you hopefully in the next few lectures this whole buzz about deep learning, that we can learn discriminant functions in very, very high dimensional spaces with amazing accuracy of results without having to resort to some complicated visualization. Okay. All right. So here's a very simple classifier. Our first classifier that we can work with, and in fact it's in your homework, right? A nearest neighbor classifier. Okay. So what a nearest neighbor classifier is going to do? There is always a training step and then a predict function. Like that's the standard strategy, right? So in the training step, the nearest neighbor classifier does nothing complicated. It simply remembers the entire training set. Okay, that's the model. The entire training set, which means all the data points and all the labels, will just be stored in memory so that I can refer to them. Now, when you give me a test image and say what label this image has, all I'll do is I'll just go through the entire training set and find the distance of this point from all the points. And then, as the name says, I'll find the nearest neighbor. Okay, and when I find the nearest neighbor, I'll say, well, what's the label of this neighbor? So if that neighbor is category cat, I'll say this point must be category cat. Okay, so that's the idea of a nearest neighbor classifier. Really, really simple and straightforward. In fact, this is the idea also. This is an example of a non-parametric classifier, because the decision information, the model, is not summarized by some polynomial or some equation or some few parameters. The entire data is there actually to describe your model. Okay. Now, non-parametric classifiers can take many other forms. It doesn't have to be the simple form, but the characteristic of them is that they don't have a concise parametric form, an equation or a concise model to describe it. You just have to store all your data to be able to know what to do with it. All right? Everyone is clear with that? Okay, so here's a data set, CFAR10 data set. It's actually quite popular in getting started with neural networks. This is really small images. I think they are like 32 by 32, right? So they are like tiny images, and they are 10 categories. Okay. So each image is labeled as one category: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. Okay, those are all the categories. And there are so there are 10 labels. There are 50,000 training images for which you know the label. There are 10,000 test images. You also know the label for them, but you are not going to use them in your training. So this is a simple data set to try to set up a neural network or some classifier and see how it works on images. Okay, so this is performance of that on the nearest neighbor data set. Now in the nearest neighbor, what I'm doing is, in this column I have a test image. Okay, this is a test image. When I take a test image, I don't know its label, but I have 50,000 of those training images, 5,000 of each category, for which I do know the labels. So I just go and compare this with all of those 50,000, and I see which one is the closest to it. And how do I compare? I use, like, maybe I could use a lot of different distance functions, but maybe I just use Euclidean distance, L2 norm. Okay, so the best match that I get from the training set is this. The second best is this, the third best is this, the fourth best is this, and so on. So that's what each row is showing. Okay, now you see, so this is actually very simple to code. There's really nothing to it, right? You just have to do a bunch of distance comparisons and find the max. Okay, now you see that even such a simple classifier is actually not doing so bad, right? Because this category is kind of similar, and it got some sort of similar characteristics. Okay, so for example, look at the ship category, and we have a lot of ship images in this. Okay, so I can say that, yeah, this is a ship category, but I do have some wrong things. I don't know what this thing is. Maybe it's a rig, oil rig or something, right? So maybe I'll confuse it with a ship. Okay, and so on. So whatever I find as the highest label, we are showing these just for example, but whatever I find as the highest label, I'll give that label to this and then see whether that's a good match or not. Whether what is my accuracy on that. Okay. All right. So how do I compare images? Well, I could use a distance metric. Let's say I use L1 distance. L1 distance is sum of absolute differences. You subtract pixel by pixel. You take the absolute value so that the negative errors and the positive errors don't cancel out each other, and then you sum that up. You have a test image, you have a training image, you subtract them, you get this pixel-wise values with the absolute sign, and then you add all of them up, so 456. So that's the similarity score of these two. Okay, or you could use L2 distance, which means here instead of absolute value you have a square, or you could use some other distance metric of choice. Okay, so here's actually code for nearest neighbor classifier. The first part, the training part, is nothing but, you see the training part here is very simple. It's nothing but just putting all the images into memory, into some sort of an array, and then the test part is you have a for loop somewhere where you are going through all the images. You are just passing through all the test images, finding the difference. Okay. And then just the Y predict is the best distance. Okay. So question: how does classification speed depend on the size of training data? It would keep on increasing, right? There is for every image that I test, there is a for loop going through all the training data set. So if the training data set is size n, I have an order n computation to just test one image. Okay. Now, let me do some variation of this very simple classifier. Let's say this is my training data. There are two features, so the feature space is two-dimensional. That's why I'm plotting it on the screen. And then I have three categories here: label 1, label 2, label 3. How do I classify this point? Well, I'll use the nearest neighbor strategy. So I'll find the distance of this point from all other points, and I realize this is the minimum distance, and so I'll label this red. Okay. So that's the strategy. We have talked about it. We'll just label with the closest label. That's why it's called nearest neighbor. What about this point? This here, the square here. Okay. Now I do realize that this is closest to red, but so the closest neighbor to this is red, but then the second closest, third closest, fourth closest, fifth closest, sixth closest, all of them are blue. Okay. So if I give some importance to the other matches, well then it's maybe not such a good idea to label this as red, right? Okay, so this gives us another algorithm. Instead of doing nearest neighbor algorithm, we do k nearest neighbor algorithm, where k is a parameter that you have to choose. So to classify example D, data point D, you find k nearest neighbors of D. Let's say k is 5. So you find the 5 nearest points in the distance metric, the 5 best distances, you find them, and then you just decide on the majority label in them. Okay? This is slightly different from nearest neighbors. Okay? So, and what is nearest, you can still have a definition of nearest. Okay? Now, if I use k nearest neighbor or one nearest neighbor, nearest neighbor is also now one special type of k nearest neighbor. So you can have one nearest neighbor, two nearest neighbor, three nearest neighbor, 10 nearest neighbor, 20 nearest neighbors. Yes, Hafiz.
So what if we could do average of all images in category 1 and find the distance mean image?
So that would be, okay, so what if I used category 1 and computed one average out of that, and category 2 computed one average out of that, and then I took distance from those averages. So that would be a nearest mean classifier, okay, rather than a nearest neighbor classifier. And yes, you can do that. Okay. All right. So now, because we talked about decision boundaries earlier, right? Let's say a polynomial boundary or the linear boundary. The question I can ask is, what's the boundary of k nearest neighbor like? Okay. And actually, in this case, it would be something like this, right? Because the distances will be affecting you. If I have one nearest neighbor, I'm always piecewise linear between different points. I'll pass through different points piecewise linearly, because if you have 2 points, the distance and the distance function is Euclidean, you'll like cut perpendicularly from the line joining them, right? The perpendicular bisector will be the boundary between those 2 points. Okay, so it's a locally defined boundary between classes and points affected. If I add another blue point here, the boundary will shift. It will go this way. Okay, and this boundary is non-parametric. It's not defined by some polynomial function or some at least some low order polynomial function. It's actually defined by the collection of these points and the distances between them. Okay, so if I have a k nearest neighbor classifier, 2 classes, x1 and x2 features, this might be my boundary. In fact, this is actually k is equal to 1 boundary. Okay, notice that this boundary is like this because of these 2 points. This line is the perpendicular bisector of these 2 points. This line is the perpendicular bisector of these 2 points. This line is the perpendicular bisector of these 2 points, because that was the one nearest neighbor strategy. Okay, so here's a comparison. I have some data of 3 categories. There are green points, blue points, and red points. Okay, and you can see it's quite noisy. It's not that they are like compactly clustered together. There are a bunch of red points here and there and so on. That's the characteristic of the data. And this is actual nearest neighbor boundary between them. Okay, the regions that can be formed by the boundaries. Okay, so everything in this blue region will actually be, any new point that you give me in this blue region will be classified in this region. Okay, and this is the boundary between them for 5 nearest classifiers, 5 nearest neighbors. Okay, in general, what you see is that the boundary gets a bit smoother with lesser kinks and small islands and so on as I increase k. Okay. All right. So, question: what's the accuracy of nearest neighbor classifier? One nearest neighbor, right? Nearest neighbor classifier on training data when using Euclidean distance. The distance function is Euclidean. I compute training error, which means I use training data and compute its accuracy for one nearest neighbor. What would be its accuracy? Best 100% or 0 error, because every point that you select now to compute error, that point actually exists in the training data, and you have a label for it. So you will assign this test point the same label because you picked the test point from the training data, which is not a good idea, but it's just so that you understand what's going on here. And so every point will be perfectly classified, and so there would be no error. Question 2, what would be the accuracy of k nearest neighbor classifier on training data? Now, this is the same question as before, except for one nearest neighbor, now I have a k nearest neighbor.
Should be ideally less than can be less than
It can be?
less than 100.
Yes, now, yeah, we can't work out because I have not shown you the data, but now there is no guarantee that you will have 100% accuracy, okay? Because you picked a point on training data, and that point exactly has one nearest neighbor near to it which has that label, the correct label, but there might be 4 other neighbors which don't have that label, and so the label of this point would change. And that's what happens when your decision boundaries smooth out, really, because of increasing k. Now you are going to ask me this question which you asked me last time, how do we choose k? And I'm going to give a similar answer as I did last time, which is like there is no good answer. Well, actually that's not true. I'll show you. In classification problems, in clustering problems, there is really no good answer of how to pick a k. When I make simple statements like these, there are always exceptions to them, so don't hold me accountable. I already gave you 5 different methods last time of people having their strategy to pick a k. So there is some researcher, he did his PhD, he came up with a very good strategy to pick k, then he listens to my lecture and I'm saying there's no good method to pick a k, and he would be like angry at me, right? So I'm just saying in general, you have to do a lot of like tweaking around in a clustering problem to understand what's a good k, because any k that you pick, k plus 1 is also a good k compared to that, unless you start penalizing higher order models. But in classification problems, you have training data available, you have test data available, so you can actually try a lot of different k's. You can take the strategy, I'm going to try a lot of different k's and see which gives me the best classification error on some unseen data. And then, so there is because you have labels available, there is a way to answer this question. All right? Okay, so coming back to this, this is nearest neighbor example for this data set. We could ask these questions: what's the best distance to use? What's the best k to use? There are a lot of choices of distance functions. There are a lot of choices of k. This question really means, in general, for any classification algorithm, every classification algorithm has some hyperparameters. So in general, this kind of means, how do I choose my hyperparameters? What are hyperparameters? I discussed that last time. These are parameters of the model itself. Not, I mean, if I'm fitting a line, the coefficients of the line are parameters of the model, right? But the fact of whether I fit a line or a curve, that's a hyperparameter to my classifier. Okay? So the immediate parameters of the model, if I fix a model, the parameters of that are just parameters. But the way of choosing the model or the distance function, those are hyperparameters. They really define the category of classifier that you would be working with. Okay? So how do we fix these hyperparameters? I mean, it's a valid question. How do I choose this k? I'm up against a problem. And the answer is that this is actually very problem dependent, and what people do is, I mean, the current practice in machine learning is often that you try a lot of them. And that's why, so one of my students here who was here, he's now working at Apple, and he was visiting, and we asked him, he's working on deep learning at Apple. And so we asked him, what do you do? And he said, I mean, what's your daily work in terms of training models and so on? What strategies do you use and so on? We were discussing like that. And he was just saying that I have like maybe 200 GPUs at my disposal on my desk, right? So when I decide I'm going to tackle this problem this way, I choose the range of hyperparameters and throw that training on that GPU cluster. And so I choose one choice of hyperparameters, we do a full learning of the network. Then another choice of the hyperparameters do a full, so it's really like a brute force attack on the choice of hyperparameter. And then once we finish that, we come up with the fact that, these types of parameters worked well. So then we take those and then we just use that training. Okay? That's like what people are generally doing in their choice of hyperparameters. An example would be in hog features. I'm doing a hog and a classifier on top of it. In hog features, should I use a histogram of 8 or 9 or 16 or 20? That's a hyperparameter. And then what I could do is, for some training set, I could use all of them and see which one gives me the best error. Now this strategy, this brute force strategy, is exponential in the number of hyperparameters. Because for one choice of the histogram length, you might have so many choice of window size, right? And then for one choice of histogram length and one choice of window size, you might have so many choice of normalization. So as you can keep increasing hyperparameters, this brute force attack on it is exponential in your expense, keeps multiplying. All right, yes, there's a question somewhere, yes. Yeah, okay, that's a very good question. जिनके पास 200 GPU नहीं होंगे जैसे हम गरीब लोग हैं, right? So what do they do? And there are very good answers to this actually. This is a good question and there are good answers to this. That's all I'll say for now. One of the strategies, for example, is transfer learning, which is a very effective strategy. You take a pre-trained network and adapt it to your problem, so you don't have to try so many different things. Okay, we'll talk about this when we talk about deep learning. It's a very the poor man's deep learning. How can that be done? Okay. But yeah, deep learning is resource intensive. I mean, machine learning in general is resource intensive, broadly speaking. Okay, all right. So, but one problem comes up. If I want to try out hyperparameters, what would be my strategy? Because I could overfit to my training data. The classifier could overfit to my training data, and then I could say, well, these hyperparameters are good, but it might be that they are just a result of overfitting. So what I should do is, I should maybe try hyperparameters on training data, train something, and then test that on test data, so as to say, are these hyperparameters good or not? Okay? It's actually a bad idea. Not only is a bad idea, it's actually a very bad idea. Okay? Can anyone think of why? Well, it's a bad idea because now you have, there was an optimization of learning the model itself. Now you put another optimization on top of it, which is learning the hyperparameters, right? Testing the hyperparameters within that learning. Now, so you are trying different test parameters within the training algorithm in a sense. So you have kind of pulled your test data into your training data. Okay, because the training is now going to be dependent on the test data, because you're going to try hyperparameter and say, this one is not good, and this one is not good. So all this is part of training. So I said in the beginning, don't let your training algorithm see your test data. Otherwise you will overfit. Now you can overfit to the hyperparameters as well as to the model itself can overfit, because during the training cycles, this is all now a big training cycle. And during the training cycle, you are looking at test data. That's bad. That can never guarantee you that later on when you start working with unseen data, it will still work well. And so what you do is you leave test data aside, and within your training data, you create another test data, the local temporary test data. Okay, so I took my training data, I broke it into 5, let's say, chunks, and I saw chunk number 5 as test data for that particular choice of hyperparameter. So I picked one set of hyperparameters, I trained on fold 1, 2, 3, 4 data set, which is labeled here as fold, and I tested that on 5. And then I picked another hyperparameter, I did the same. I picked another hyperparameter, I did the same. Okay, and I kept doing that till I settled on some hyperparameter for this training set. Now I go and measure the performance on the test set. And I say, this is the performance of my classifier. Is it good or not? Otherwise you retrain. Okay? Except, yes, are there questions? I'll come to except later. Go ahead.
So in this approach you're setting up hyperparameters by using any of the folds as the test set. What if on the test set the hyperparameters that you've chosen do not perform?
Well, if you kept the test set separate, then yes, you can overfit here, but the test data will go bad, and so you will know, right? The same curves that I showed you hold for the test set now. So you will see on the test set where you worked well. Okay, but the choice of the hyperparameters for that fold of training set will be decided. Yani the entire training process will be done for one choice of hyperparameters. The entire training process. Okay, so let me say this again. There's a bit of confusion here. Okay, let's say I have to choose k, or take another example. I have to choose the order of my model. The order of my polynomial model. Should I use a polynomial of order 3 or 4 or 10? Okay. So I first make a choice of the hyperparameter, order 3. Now on this order 3, I still have to train and ensure that the training is not an overfit. That's going to be done by these green and yellow parameters. Okay. The green and yellow will ensure that when I choose k is equal to 3, whatever fit I got of the polynomial was not an overfit, because if I did an overfit, the fold would give me the unseen part for that k is equal to 3, the unseen part would give me bad error. Okay. Now I do k is equal to 4. I can still do this here for k is equal to 4. Okay. But for each of those, k is equal to 3, k is equal to 4, k is equal to 10, whatever is the best model that I get, I can test on this. This ensures that within that changing of the k process, I'm not doing an overfit. Okay, because I'm using completely unseen data. So it's like a nested structure that I've built. Okay, and that's how I will tune for my hyperparameters. Yes. Yeah, I didn't say what are folds. So yes, it's just one chunk, and I divided it into 5 chunks and used one of them as. Yeah. No, training data is the only data which is labeled. Okay, so everything actually is training data. I first separated out test data from it because it's labeled. I can't use the unlabeled data because I wouldn't know what is the error on it. Okay, all right. Now, one last thing that I want to say here about this topic, not last overall, is that because I'm leaving out data, I get left with less and less data set. Okay, so if you have less data to train, your training will not be as accurate because this is essentially statistical training. So if the sample size is small, you will have more noise in your estimator in general, right? So one strategy we do is we repeat this process while changing this fold, while changing which one of them is the test data for that iteration. Okay, for that chunk. So first I will pick this as validation data and train from these 4. Then I pick this as validation data and train from these 4. Then I pick this as validation data and train from these 4. Okay, and I keep averaging out my result of error. Now that ensures that all the data will be used also. It increases my time, but it ensures that all the data will be used. I won't be left with a very small data size, and the result will be averaged out. The accuracy will be averaged out. Okay, so this strategy is called what is it called? Yeah, okay, I didn't need to write it, it's written here. This strategy is called cross-validation. Okay, we cycle through the choice of which fold is the validation fold and average the results. This is a very popular strategy. 5-fold cross-validation or 10-fold cross-validation is often used. Yes?
Are you averaging your hyperparameters?
No, I'm averaging the error to find the total combined error for that choice of hyperparameters. Because when I use fold 5 as my validation fold, I'll get some error of the trained model. Then I use fold 4, I get some other error, and I keep doing that. Well, essentially, if the data was completely homogeneous and large enough, essentially I should have gotten the same error regardless of what choice of data I took. So I average them out to get like one number. Okay? Is this clear? Yeah. Yes.
Then the next time you build on the same one, but you start again.
You start again. Free. You start again. Okay. There are many variations to cross validation. Well, one is how many folds you use. So this example on the screen, I would call it 5-fold cross validation. So if somebody asks me, how did you do I report some error. So this is very typical in papers or in discussion. People say, okay, what was your error? I say, this is the error I was getting. And he said, well, what is your training set size? What is your test set size? And how many folds of cross validation are you using? Just to understand what training they did. Okay. I could use 10-fold cross validation, 5 or 10. These are very common numbers for cross validation. Yeah. Yeah, it's a hyper parameter. Very hyper. This is just to maintain statistical accuracy of the estimate that you are getting, the estimate of the error that you are getting. Yeah. All right. So I've given you an introduction of supervised learning. Okay. Let me talk about a particular category of learning algorithms, which are linear discriminant functions. Okay. These are very important to study for two reasons actually. One, that it's a simple category to learn because you will restrict all possible linear functions, all possible decision functions that you could have gotten, all possible categories of discriminant functions that you could have gotten. You restrict yourself to the linear category. If your data is two-dimensional, that means it's a line. In fact, let me start from the beginning. If your data is one-dimensional, a linear discriminant function is a point. It's a threshold. This way you have one category, that way you have another category. We are right now talking about two category problems. If your discriminant function is, if your data is two-dimensional, yani you are measuring two features of your data, then it's a line. If you are measuring three features of your data, it's a plane. If you are measuring n features of your data, it's a hyperplane in an n-dimensional space. Okay? So in general, it's a linear function in a d-dimensional space if d is the number of features. Okay? Okay, so what's a linear discriminant function like? Well, this is a linear discriminant function. In fact, this is a pretty nice data set. I can actually find a function which is find a linear function which exactly gives me 0 error on this data, which is what I've drawn. Okay, there were a few problematic points very close to the line, but okay, I'm kind of good. All right. So when I say linear discriminant function, well, first thing, discriminant functions are split of the feature space, some sort of split of the feature space. Linear, the ones where the split is linear. Okay. Now what is so special about this particular orange line? Well, I could have drawn an infinite number of orange lines on this space, right? Those are the possible solutions that I am kind of learning through in my training algorithm. I fixed that my discriminant function is going to be linear. I fixed that, but then I could have drawn a lot of linear functions. So I draw kind of all of them and compute their error, and then find the one which has the least error. Except I could actually do this in closed form. I don't have to try all of them. I could do this through calculus. Set up a cost function and minimize it, and you can find this. Like you do regression, you can also do this. Okay. All right. So I'm throwing a lot of basic machine learning concepts at you today, just to build like a foundation on which we can talk about machine learning. Okay, so there are two types of approaches that are very common in trying to find this linear discriminant function. Okay, two category of approaches. One is generative and one is discriminant. Okay, the generative approach is to estimate the discriminant function by first estimating the underlying probability distributions of each class, and then saying where those probability distributions kind of intersect, that's where my boundary is going to be. Okay, and the discriminant approach is to compute the discriminant function directly instead of actually finding the underlying probabilities. Okay, let me show that to you with an example. What is a generative approach? Okay, so this is kind of example of a generative approach. I have so I think today my pen is not going to work. Well, sometimes it works, sometimes it doesn't work. I don't know why. Okay, so I have two classes here. There's a blue class and a red class in a two-dimensional feature space. Okay, and you can see that the boundary should be somewhere here. Okay, but how do I estimate the boundary? First, I forget about the red points. I just take the blue points and find its histogram. Okay, and that histogram is this, we call it P of X given the category. So if the category is 1, then this is the histogram. It's a Gaussian distribution actually, because the points in the middle are more dense. In fact, I generated these points randomly through a Gaussian distribution. These are normally distributed random numbers in 2 dimensions, independent in 2 dimensions. So when I estimate the PDF, it actually comes out to be a Gaussian distribution, and then I estimate the other PDF just for those points. That's what it's meant by conditional probability. The probability of the variable X given the class as 1, and so that means no red points, and the probability of the variable X given the class as 2, which means no blue points. So I independently estimate those 2 probabilities. Those are 2 Gaussian functions, and then somehow I find what's the best way to separate those probabilities, and I can actually do that in closed form. I can find the best separating line between them, and once I find that line, on one side is region 1, one side is region 2, and that's my trained classifier. Okay, so I'm actually going to show you I'm actually going to show you how we can compute that line. Okay, so here's an example. Let's say my problem is I have to classify 2 types of fish. So I'm a fisherman. I go to sea and I cast my net and I pull out fish, and there are actually 2 different categories of fish. So one is salmon and one is bass. Okay, sea bass. Okay, now it turns out that maybe salmon is more expensive than sea bass. So if I ship them in tins, and somebody buys a salmon tin, and then when they open it, it comes out to be sea bass because I just randomly assigned them labels, they're not going to be happy, right? They said, well, I wanted salmon, or maybe they like the taste of salmon better than sea bass. Okay, so I have to build a classifier to be able to do this, because I can't do this on my own, so that I can put them in the correct tins. Okay, so that's the problem. Okay, so what I do is I measure some feature of my fish. Let's say that feature is length, because it turns out that in general bass is bigger, longer than salmon. Okay, so I plot. I have some training data. I mean, a bucket full of salmon and a bucket full of sea bass only, right? So that means that's labeled data. Okay, so I go about measuring the feature and building a histogram of it. A histogram is like a probability distribution, right? So I measure all my salmon in the first bucket, and I found out that their histogram we found out that their histogram of length is like this. And then I measure all the sea bass in the other bucket, and I found out that their histogram is like this. Okay, and so this histogram kind of encodes information that sea bass in general is longer than salmon. And so the classification strategy that I'm going to take is I'm going to mark a threshold somewhere between 20 and 40. And each fish which is longer than the threshold, I will label it as sea bass, and each one which is shorter than that threshold, I'll label it as salmon. Okay, that's a linear classifier in 1 dimension, and there is only 1-dimensional data because I'm measuring one feature. which is length. All right? It seems like a good strategy, right? Okay. So the question is, where is the optimal threshold? I want to find the best threshold, provenly optimal, which means I want to find the best classifier for this problem. Given that I can only measure this one feature, I want to find the best classifier for this problem. No, it should be provenly optimal. Okay, so I'll overlap these histograms, and maybe I'll say that the best, threshold should be somewhere here. In which sense is it best? Well, I'll still get some errors. There will be some small CBAS, which is given by this portion of the curve, and there's some very like hyper elongated Salmon, like the good ones. They are actually here. But if I draw the threshold anywhere else, I'm going to get more error. Okay, so I actually want to mathematically get to this the correct form of this threshold, okay, or the correct form of the linear discriminant function. Oops. Okay, so I'm drawing the same figure, but I'm talking now the language of probability. What is the probability of length given Salmon? That is what my histogram really is. Yes.
So isn't optimal place dependent on the situation at hand? Like if we were very cautious while we didn't want to send bash instead of slamming, the approach of threshold value.
Yes, that's actually true. If the cost of making an error is unequal, then I should bias my decision towards which class is more expensive. I should bias my decision towards that. So I'm assuming, I'm assuming a lot of things here. I'm assuming equal cost of making an error, and I'm also assuming equal likelihood of catching a fish. If it was that in the sea there were 90% Salmon and only 10% sea bass, then the optimal decision is not exactly in the middle, right? Because if I put it in the middle, I'm actually making more errors on Salmon because they are just more frequent. Okay, so we are going to derive the optimality here. Okay, all right. So this histogram is really nothing but, if I write it in the language of probability, it is nothing but probability of length given Salmon, because it's only for the Salmon fish. Okay, and this is nothing but the probability of length given bass. There is one other thing. The histogram is an approximate to the density. The density function might be smooth and continuous, and the histogram will have bins. But other than that, they are essentially the same thing. The histogram, actually, we can say the histogram is an estimate of the density function. It's an estimator of the density. Okay? All right. So we are interested in knowing P of Salmon given length and P of bass given length, and I can measure that by histogram or by some other density estimation technique. There are a bunch of other density estimation techniques that I can use. But histogram is one of them, so let's just keep it simple. I made the histogram and I said, well, that's the density. Okay. Okay, so, oops, I have some auto forward. I didn't make this point clearly. So what I have is P of length given Salmon and P of length given bass, which is the histogram. But what I'm interested really to make a decision is the opposite of that. I want to know what is the probability. I'll catch a new fish. So I know length now for that. Let's say the length is 30. Well, 30 is a bad number because it's exactly in the middle of 20 and 40, the example I was given. Let's say the length is like 37. Okay. What I want to know is, what is the probability, the opposite of this really, what is the probability that the fish is Salmon given that the length now is 37? And also, what is the probability that the fish is sea bass given that the length is 37? That's actually what I'm interested in, but I don't have that. From this training data, this is what I have, right? I don't have that. But if I knew these two probabilities, I'll see which one is higher, and I'll say, well, that's the category for this new fish. Okay? So the question is, how do I reverse these conditional probabilities? That's really the question. If I can do that, then I will know my answer as the max of these two numbers. Okay. Do what? I can use Bayes' rule because that's what Bayes' rule does. Okay, so everyone who has taken probability would have seen Bayes' rule. So let me just state that here. What is Bayes' rule? Bayes' rule is probability of A given B is probability of B given A, probability of A divided by probability of B. Okay, so in our example, the probability of category 1 given a measurement x, let me put words to it, the probability of salmon given x, a length, which is what I want to find out when given a new fish, is equal to the probability of that length given salmon that I have from the histogram times the probability of salmon itself. If I just randomly caught a bucket from the sea, how many would be I randomly caught 100 fish from the sea, how many would be salmon, how many would be bass? That's what this guy is. We call this the prior probability. Okay, divided by the probability of the length being 37 itself. Okay, so in words we call this the a posteriori probability, because it's like the reverse, which is equal to the likelihood, which was that histogram, times the prior divided by the evidence. Those are the terms, that English terms that we use for them. Omega here is the class. It can be omega 1 salmon, omega 2 sea bass, and x is an observation length. Okay, so the example is this: probability of salmon given length of 23. I want to find that, equal to the probability length is equal to 23 given salmon. That you can read from a histogram. Probability of salmon, that's the prior. How many salmon would you have caught anyways as a percentage? Prior probabilities exist even before you have caught a fish, even you have caught a new sample. Okay, that's just how many salmon there are in the sea. I need to know that, divided by the probability of length 23. Okay, so my optimal classification strategy would be, I can prove, actually I'm not proving that here, but I can prove actually that this strategy, if I find probability of salmon given length 23 and probability of sea bass given length 23, if I can compute that and I decide on the maximum of them, this is provenly the optimal strategy which will give me the least error rate, provided the cost of making an error is equal. So we call that risk in Bayes theory. So provided risk is equal, this is the optimal strategy. In fact, this is the optimal classifier. You cannot make a class, you can prove by taking derivatives, putting equal to 0, find the least error that this classification strategy is provenly optimal. There exists no classifier in the world that can do better than this. Okay, so Bayes classifier is the optimal classifier. The classification strategy is, given an observation x, p omega I given x for all I, we compute that, the posterior probability, and we classify the class which returns the highest probability. So in mathematics, really my label is going to be the maximum I, the value of I which gives me the maximum probability, p omega I given x. But p omega I given x by Bayes rule is nothing but this. And now you see that the denominator term, the evidence term, actually doesn't depend on I. So I can drop it, the decision will not change because there is no dependence on I of the measurement here. So I really don't need that. So I can drop it, and so this is the optimal strategy. I compute px given omega I, which is from my training, my histogram, multiply that by p omega I, which is from the prior. I read that length from the histogram, multiply that by the prior, find the posterior probability, the something proportional to the posterior probability because I don't have px now. And then I compute the other one, take their max, which one is the maximum, that's the label, and that's the optimal classifier. Yes, there's a question there.
So if you build this classifier, the custom error will be 100% accurate, or will there be some minor errors? Any minor errors?
There will be errors, right? Because notice that the histogram were overlapping. So if that's the case, you'll measure a length, let's say 30. There are some fish which will be salmon and they are length 30, and there are some fish which will be bass that are length 30. So you'll decide one of them. The other one will be an error, right? So there is going to be some error rate in this. But what you can prove is that there is no better classifier that exists that can give me less error than this strategy. Okay? That error is called actually Bayes error. That form of error is called Bayes error. It's an inherent error in the problem, and actually you can't do anything about it.
What if the histograms do not overlap? And there's no error?
If the probability density functions don't overlap, yes, then there should be no error. Yeah, that's true. That rarely happens. Okay, one question here. If this is the optimal strategy, then we should be done with machine learning, right? We just need anybody who's working on machine learning. I mean, what I talked about classifiers for about an hour, a bit more actually. Okay, but that's all you need to learn about machine learning, right? Because in that amount of treatment, we reach to an optimal classifier, and provenly there cannot be any better classifier. So I mean, why do people take courses and on Coursera and here and so on, and what is the hoopla about? Okay, so that's a good point. We don't know this distribution to begin with. And sorry?
We might not know the likelihood and
Yes, we don't know the px given omega i's, and we might not even know p omega I. And in fact, as we will see, let me just finish this slide. And okay, so the base classifier is optimal. There is no need to search for a better classifier. But number one, it is optimal given a feature set. This was optimal for the feature set that the length is the feature of choice here. It might be that if instead of length I was measuring weight, then I actually get two histograms which are more separated from each other, so I get more better classifier, less error. It might be that if I use length and weight both, I get even less error. It might be that if I measure the color of the eye, that's distinguishable. Or if I can measure how many scales there are on the skin, that might be a distinguish. Or if I can count the number of fins, that might actually give me better error. Okay, so well, one thing, base classifier is optimal only for the feature set, and the second thing is that the ideal PDF of that feature set is known for each class. This is almost never the case. We will see why. I mean, why is that such a hard problem? But this is almost never the case that I can find these ideal PDFs. And so we have some more lectures to talk about. We won't finish machine learning here. Yeah.
So we're talking about two categories here. What if it counters a new category like another kind of fish? Let's still classify that fish into one of these two, or let's say that it's none of them.
Yeah, that's the question of reject class. So right now we are assuming that there are only two types of fish in the sea. If we make that assumption that there are only two types of fish in the sea, and I actually catch a third fish sometime, that will be categorized as one or the two, because I didn't leave a choice of not choosing a label, because whichever probability is the max, I will choose that label, right? Now what you can do is one way around that is that you can have a reject class. You can say only if I am so much on the histogram minimum value will I label it as one of the class. If I'm like very far away, like the histogram is 0 there for both categories, then I'll say, well, that's not really anything that I've seen before, and I'll reject it. Okay, so you can have a reject class built into that strategy. All right, we will finish here today. Any other question? Okay, done. So we have a quiz. You can take this. I think take half of these and just sit down and just pass them back, and take half of these, and yeah, can you take this and pass them back?